students, in last class, means lecture 1, we discussed about some basic concepts of fluid mechanics, and we are going to continue two concepts regarding to the basic concepts of the fluid mechanics, and then we are going to start viscosity in our lecture 2. So today we are going to discuss about isothermal bulk modulus of an ideal gas and adiabatic bulk modulus of an ideal gas. So here, when we come to the isothermal bulk modulus of an ideal gas, for ideal gas equation is PV is equal to mRT. So if we rearrange the ideal gas equation, we are going to get the isothermal bulk modulus equal to pressure. How it is? Now here we can write as P is equal to this V, if it's come here, P is equal to M by RT, and P is equal to mass by volume is density and RT. So in last class we came to know that K is equal to bulk modulus is equal to rho into dP by d rho. So if we consider as a means here, if again we should we should do derivative of the this we should do derivative for this equation with respect to density. dP by d rho is equal to RT. So we use this dP by d rho equal to RT here. So we will get isothermal bulk modulus equal to rho into RT. So this rho RT will gives rise to pressure. From here we will get isothermal bulk modulus equal to pressure. So you should, this is a simple thing, so you should try to remember, because in some competitive exams you will have lack of time, you don't have a sufficient time. So next, adiabatic bulk modulus of an ideal gas. So adiabatic gas equation means PV power gamma equal to C. So in PV power gamma equal to C. So to get a adiabatic bulk modulus of an ideal gas, first we consider Cp, specific heat at constant pressure, is always greater than Cv. This is everyone knows, but I want to explain once. So why specific heat at constant pressure is more than the specific heat at constant volume? Suppose considered at a constant volume, you are going to add heat. Constant volume. So all the energy you supplied will be used into increasing the internal energy of the gas. This gas internal energy will increase, but there will be no external work done. But when you heat a gas chamber at constant pressure, if you heat at constant pressure, the heat uses to increase the internal energy of the gas, and also it expands and increase the volume. So some external work done is happened. This is CV condition. This is CP condition. So in both cases internal energy is there, but the external work done is in the case of constant pressure condition. So we will consider Cp is always greater than Cv. So Cp by Cv is greater than 1, that is gamma greater than 1. So gamma equal to Cp by Cv. This if we again we consider density is equal to mass by volume. Rearrange equation, volume is equal to mass by density. If you substitute this in this first equation, if you substitute this one in this first equation, you are going to get this. Again, if you rearrange this, P by rho power gamma equal to constant by m power gamma, that is P power rho gamma equal to constant. That implies pressure is equal to C rho power gamma equal to C rho power gamma. So if you differentiate with respect to density, it will be converted to dP by d rho equal to C gamma rho power gamma minus 1. So if we rearrange all these, we will get adiabatic bulk modulus is equal to gamma P So isothermal bulk modulus is pressure. Adiabatic thing is gamma into pressure. So if you divide both these Ka by Kt, you are going to get, sorry, pp cancel, you will get gamma, that is this one. The ratio of adiabatic bulk modulus to the isothermal bulk modulus is equal to gamma. So if we simply remember these two equations to do the problems as fast as possible. Adiabatic the bulk modulus is gamma p, isothermal bulk modulus is only p. Now we are coming to today's topic, viscosity. It is the internal resistance offered by the one layer of the fluid to the adjacent layer. Means this layer will have an internal resistance between the another layer. So here you consider a fluid flow stream. Here there was a fluid flow stream. So consider certain point in certain area of the fluid flow. If you zoom this one, it will be this, and you consider here this is the distance dy, okay, and the velocity means means suppose here there is a plate, the fluid velocity will be here, it will be less when we are going to farther to the from the plate, velocity will be high. That is why if there is a u velocity here, there will be u plus du velocity here, and velocity is equal to distance by time. So this distance you will get du into dt, distance is equal to du into dt, and this way angle will be d theta. So tan d theta equal to opposite by adjacent, du by du dt by dy. This one we got. Next, so if d theta is so much small, tan d theta will become as d theta. If the angle d theta is small, it will be always small, so tan d theta equal to d theta. So d theta will become equal to du dt by dy, and if you rearrange d theta by dt equal to du by dy, and shear stress will be equal to force per area. So shear stress is directly proportional to d theta by dt, and shear stress equal to this proportionality symbol, if you remove it will become viscosity, viscosity into d theta by dt, and mu equal to shear stress by d theta by dt. Okay, if shear stress is same, suppose consider two conditions a and b. If shear stress is same and d theta by dt is very small, if this is very small, this is obviously this is going to be more. This is same for both condition. If this is small, means if it is very small, resistance is large, flow is tough, and mu is large. Here you can see, if d theta by dt is large, viscosity is less. If this d theta become large, means there is no stress resistance, so this flow is more. So d theta by dt is large, the flow is easy, resistance is less, mu is less. From this equation you can know, if the stress is same, you can consider, you can know the how relative viscosity between the two stream flows. Okay, next, mu represents the internal resistance offered by one layer of fluid to the another layer adjacent layer. This is called viscosity. The mu is known as coefficient of viscosity or absolute viscosity or dynamic viscosity. Viscosity is also of two types, dynamic viscosity and kinematic viscosity. Okay, shear stress is equal to mu equal to d theta by dt, that is equal to shear stress is equal to mu equal to shear stress equal to mu into du by dy. Why? Because this is velocity gradient. This is rate of angular deformation, means rate of shear strain. So we can compare these both two. So shear stress is equal to mu into du by dy. What is Newton's law of viscosity? According to the Newton's law of viscosity, shear stress is directly proportional to rate of angular deformation or rate of shear strain. Fluids which obey Newton's law of viscosity are known as Newtonian fluids. Air, water, petrol, diesel, several these are called. This all obeys the Newton's law of viscosity. So these are called Newtonian fluids. Next, for a Newtonian fluid, the equation is the shear stress is equal to mu into du by dy. This we know already now. Just now we have seen. Hmm? So if you plot a shear stress in y-axis and du by dy in x-axis, if you plot for air, water, and oil, air has air has less theta, water has more theta, means more angle. Greater slope, the greater viscosity. If this is greater the slope, means slope is y2 minus y1 by x2 minus x1. If slope is more, here you can see slope is more, here slope is less. If you are going like this, slope is also increasing. If greater the slope, then greater the viscosity. Okay. Variation of viscosity with temperature. In case of liquids, the intermolecular distance is small and hence cohesive forces are large. So, in case of liquids, suppose there is a liquid, okay, the intermolecular distance is small. There will be small intermolecular distance between distance is small. Hence, cohesive forces are large. With rise in temperature, these cohesive forces decrease and hence resistance to flow also decreases. So, in case of liquids, mu decreases with increase in temperature. But in case of gases, it is different because the intermolecular distance is large and hence cohesive forces here will be going to be negligible with rise in temperature. Molecular disturbance increases and hence viscosity also increases. In case of gases, mu increases with increase in temperature because the molecular disturbances increases. Means the molecular disturbances between, if it is a gas, the molecular disturbances and increases and the viscosity also increases. So you can see here the plot. With increase in temperature, the viscosity in liquids is decreasing, but with increase in temperature, viscosity of the gases is increasing. For fluids, so viscosity depends. For fluids, means liquids and gases, both will be considered. It is a function of cohesive force and molecular agitation. For gases, means I just don't know, for that is its explanation is kinetic energy equal to 3 by 2 kT. So kinetic energy is of mv square. This is 3 by 2 kT, and this is constant, this is constant, this is constant, this is constant. So V square is directly proportional to temperature. With increase in temperature, molecular agitation increases, velocity increases, so that the viscosity also increases. This is for today's class about viscosity. We will continue our next concepts in our next lecture. Thank you very much for watching. Please comment, subscribe, like and share. Thank you.